So we have been talking about the closed system where particles in a system are confined and there's no particle leaving the system or nor the particle is entering the system. Okay, now in this chapter we'll talk about the particles actually entering the system. Okay, the system is open, so that the particles from outside surrounding can enter the system. So when we add some particles to a system, there would be some interaction between the added particle and the already existing particles, and due to which the internal energy of the system increases. Okay, and the energy that is being added to the system due to the addition of the particles is proportional to the number of particles, or you can also say number of moles added to the system. Okay, and the energy added to the system is denoted by mu times n. Okay, where mu is called the chemical potential. So here we are talking about open system. And again, it's the system in which particles can be added. Okay, and due to the addition of the particles there is increase in internal energy. Of the system, and this internal energy is proportional to the number of moles you add. Okay, so the total energy added to the system is given by mu times dn, and this mu is called chemical potential. And this chemical potential is associated with intermolecular interaction or intermolecular force. Intermolecular force. Okay, so initially when the particle is far away from the system, there is no interaction. You can say the potential energy and kinetic energy of the particles is zero, and when you bring the particle, or when the particle comes close to the system or the particles in the system, then the potential will of these particles attract the outside particle. Okay, and as a result the particles, the particle in the vicinity of this particles in the system gain kinetic energy. So this one gains kinetic energy at the cost of the potential energy. So initially the potential energy plus kinetic energy is zero, and because there is a negative potential or potential well associated with these particles in the system, so the particle that you're adding to the system gains kinetic energy, which is equal to the negative potential energy. Okay, as if the particles fall in the potential well, gaining the kinetic energy. And as these particles, the particles that you add gain kinetic energy, they collide with the particles in the system, and during the collision these particles impart their energy to the particles in the system, and that's how the particles in the system gain kinetic energy or internal energy after you add the particles in the system. Okay, so if you want to draw the potential diagram for the particles you're adding, so initially at the distance infinity, when the particles are infinitely far away from the particles in the system, the kinetic energy and potential energy of the particles are 0, and then when you bring it close to the particle, it falls in the potential well. Okay, so initially there is attraction, and then it gets attracted at up to a certain point, okay, up to this r is equal to r naught, and then after that there is repulsion. Okay, there is a strong repulsion. So again here this kinetic energy is added to the internal energy of the system. Okay, now let's say we want to find the magnitude of the chemical potential nu. So to find that, let's look at an example. So let's say you add some sulfuric acid to water, and we know that when we add sulfuric acid to water, it's exothermic, so it produces some heat, giving rise to the temperature. So let's say we are adding 10 to the negative 5 kilomole of sulfuric acid, H2SO4. We're adding it to water. Let's say that's 5.56 times 10 to negative 2 kilomole of water at room temperature. And as a result, so there would be again increase in temperature increased by 0.0 degrees Celsius, 0.1 degrees Celsius. So here we assume that the interaction between the sulfuric acid molecules are smaller compared to the interaction between the sulfuric acid and the water molecules. And the specific heat capacity of water is 7.52 times 10 to 4 joules per kilomole per degree rise in temperature. So that means the heat gained by water would be mass of water times specific heat capacity of water at constant pressure times change in temperature. And here the mass of water is, in terms of moles, it's 5.56 times 10 to negative 2 kilomole specific heat capacity of water is 7.52 times 10 to 4 joules, and the change in temperature is 0.1 degrees Celsius. So this gives us 418 joules. Okay, and since the mass of water is more than 1,000 times the mass of the acid, so that means we can ignore the specific heat capacity or heat capacity of the sulfuric acid. We assume that the sulfuric acid doesn't absorb any heat. Heat is mostly absorbed by water. So then the chemical potential of the water, or chemical potential of the gained by the water, is heat absorbed per mole. Okay, that's the chemical potential, heat absorbed per mole. And here this negative sign is because of heat transferred from acid to water. Okay, so here we are finding the chemical potential of the acid in water when we add acid in water. Okay, so that's why we have negative sign here, because this is the heat lost by acid to water. So negative 418, which is also the heat gained by water. So here we found heat gained by water, but that's also the heat lost by sulfuric acid. So just reverse the sign and then Q would be exactly same as that. So delta N is 10 to negative 5th. So that gives us negative 4.18 times 10 to 7 joules per kilomole. Okay, so sulfuric acid loses that much heat per kilomole when you add to the water, to that many kilomole of water. So that many kilomole, where is that? That many kilomole of water. So and this is for each mole of the H2SO4, but we are often interested in the chemical potential per particle, okay, or per molecule. So since water has 6.02 times 10 to 26 molecules per mole, so that means the chemical potential per molecule is given by this over the Avogadro's number, which would give us negative 6.94 times 10 to negative 20 joules. If we divide this by charge, then that would be negative 0.43 eV. Okay, or this, if we divide this by 1.6 times 10 to negative 19 coulombs, okay, charge of an electron. So that will give us the energy, electron volt, energy of an electron, energy per unit electron, which is electron volts, or potential of one electron. Okay, so now so when we write the internal energy, because we are now considering the open system, so we cannot just write du is equal to TdS minus PdV. Okay, this is for the closed system, but for an open system we also need to consider the energy, the change in energy as a result of adding or subtracting particles. Okay, so that means we need this mu dn, which is due to the chemical potential. So here dn is change in number of moles, a change in a number of molecules or particles, I should say, in the system, okay, which gives rise to this change in internal energy. So here we see that U is function of S, V, and N. So we can write the change in internal energy as, or the differential of internal energy as partial S, partial U, partial S. Now here we need to keep two variables constant, so V and N constant, ds plus partial U, partial V, keeping S and N constant, dV, plus partial U, partial N, keeping S and V constant. Let's just erase that. Let's see. So that's dn. Okay. Now, so we can get the definition of mu by comparing these two equations. So we can compare the coefficients of these differentials. If we do that, then coefficient of dn is mu would be that. Okay, so partial U, partial N at constant S and V. So that means chemical potential is basically change in internal energy when you add some particles in the system. Okay, change in internal energy per kilomole added to the system. And the condition here is at constant entropy and volume, or keeping the entropy and volume constant. So basically mu is change in internal energy of the system when you add some particles in the system, keeping entropy and volume constant. Okay, so that gives us the definition of chemical potential. Now, so that's the condition when we add only one type of particle, but sometimes we may also add different kinds of particles. Okay, multiple types of particles. In that case, this equation will become, so when more than one type of particle is added to the system, then you will have du is equal to TdS plus TdS minus PdV. Now for multiple species of particles, we need to, for each species we need to do this, add this mu dn. So we have multiple mu dn's, so we can write mu j dnj, where j goes from 1 to m. Okay, so that's the number of species. If we have 3 different types of particles, then this would go from 1 to 3. And then with that we can again define the chemical potential for each species of particles as partial u partial n, keeping s and v constant, and also the number of other species constant. So if we are considering the jth species of the particles, then all the other numbers would be constant. Okay. Okay, so now let's talk about a theorem from math called Euler's theorem. So Euler's theorem for any homogeneous functions is that if you scale some function, scale means if you multiply a function by some constant number, then if that results in the scaling of each variable of the function, let's say you scaling the function scales the individual independent variables, that then you can write the function as independent variables times partial f partial x plus independent variable y partial f partial y plus independent variable z partial f partial z. Okay, so that's the Euler's theorem. And actually you can get this one pretty easily. So if you differentiate this equation with respect to lambda, and then suppose that lambda is 1, you will get this function. Okay? So you do the differentiation with respect to lambda on both sides, and then substitute lambda by 1, so you get f on this side and then that on the right side. So let's use that for our internal energy. So when you add particles to a system, so let's say our function here is u, and u is a homogeneous function, a homogeneous function of s, v, and n. Then using this theorem, we can write u is equal to s partial u partial s, keeping v and n constant, Okay, we are adding only particle we are adding different kinds of species here. Okay, and then this is V, partial U, partial V, keeping S and N constant, and then here sum of all the terms due to the different species of the particles. So partial U, partial Nj, keeping S, V and Nk constant. Okay, so this is for one particular kind of species, and then we are adding such terms for n number of species. So J goes from 1 to m. And we already got the differentiation of U, or differential of U, before. So we previously showed on this, in this expression, between these two expressions, we have here this thing is equal to T, comparing the coefficients of ds, and this thing is P, negative P, and this thing is mu. Okay, that's what we have. So let's rewrite that again. Okay, so then we have partial U over partial, I'm just rewriting this from the comparison of the coefficients. So Vs, Vn k that is equal to T, and then partial U, partial V, keeping S and Nk constant, is equal to negative P, and then partial U, partial N, keeping S, V and all the other species, number of other species constant, just changing one number of one particular species. That gives us the chemical potential due to that particular species. Now if we substitute all these results in this expression, okay, so substitute this here and this one here and this one here, what we get? So then we get U is equal to ST minus VP. Okay, that's V and this thing is P, and then plus summation that goes from J is equal to 1 to M. This thing is mu J and J. Okay, so that's the internal energy expression. Now we have the definition of the Gibbs function. So definition of the Gibbs function is U minus ST plus PV. Okay. So using that, we can now substitute this U by that expression. So if we do that, what we get? So we get G is equal to ST minus VP plus J is equal to 1 to M mu J and J minus st plus pv. Let's see, something is missing. So this is p, sorry, not d, p. So vp and pv cancel, st and st cancel, so g will then be summation j is equal to 1 to m mu j and j. So this is the Gibbs function. And this is for the multiple species of particles. Now if you have only one kind of particle, then you can write this as g is equal to mu n, okay, just for one kind of particle. And you can write mu, which is the Gibbs chemical potential. This chemical potential mu would be then g over n. Okay, so basically we can also define mu or chemical potential as Gibbs function per mole. Okay, now so let's take the differential of this equation. So we have again u is equal to st minus pv plus summation mu j, and j goes from 1 to m. So let's take the differential du. So du is equal to sdt plus tds minus pdv plus vdp plus summation mu dn plus n d mu. Okay, and then this is the differential, and we also have another differential for u, which is, let me rewrite that here. So we already got this one from the previous treatment. So we have TDS minus PDV plus mu j d and j. Now if we equate these two expressions, because both are du, so let's equate that. SDT plus TDS minus PDV plus VDP plus mu j d and j plus nj d mu j, that is equal to TDS minus PDV plus mu j d and j. So then you can cancel TDS and TDS, PDV and PDV, and mu j d and j, mu j d and j. So then what is left? So then we'll be left with SDT minus so we have minus here, that means this needs to be right. So this is minus, so this needs to be negative. I think I didn't consider that sign, so let's go back and see. Yeah, so we have PV here, so if I take the differential, both the terms should have negative sign, so I need to make that correction here, so negative sign. So then we have VDP, that's equal to all the terms on the right side are cancelled, so we have that on the left side, so summation nj d mu j, okay, that is equal to 0. So this is a very important relation or equation called Gibbs-Duhem equation. So here mu, so j goes from 1 to m, so this is called Gibbs-Duhem equation. Okay, now we have the expression for g, which is mu j and j, where j goes from 1 to m. So if I take the differential of that, so dg would be taking the product rule, so mu j d n j plus nj d mu j So if I consider the temperature and pressure to be constant, okay, say T and P are constants, keeping these things constant, then this expression will give us Nj d mu j to be 0. Okay. So at constant temperature and pressure, so this dg would be equal to, so this thing is 0, which is that, so dg would be equal to mu j dnj. Okay, g goes from 1 to m. So this is very important relation, so we will look at an application of this in the next lecture.